Hello everyone. Today I'll be talking about topological quantum computing. As you may have heard, Microsoft recently announced that like a chip that they said could hold like 1 million qubits or something like that. That statement is kind of more of a marketing thing where like investors like to see a big number, but what's really interesting is that Microsoft's quantum computer is a topological quantum computer. And what's really interesting about their press release was that they claim to have made progress on creating uh, topological qubits. And so today I'm gonna discuss what topological quantum computing is and why it's exciting. So yeah, but before we start, an announcement. We have a big event coming up soon called Spring into Quantum, which is basically celebrating the year of quantum. We're going to have networking, a poster session for people to share their research, speakers, and more. There'll be refreshments, and it'll be on Friday, April the 4th from 3 to 7 p.m. Zach, do you have anything else related to this?
Not much. I guess we're going to have registration forms out very soon, which you can find on our website at that QR code. Forms for any attendees and for people that want to present posters.
All right, cool. So what exactly sets topological quantum computing apart from other types of quantum computing? So you might have heard of, for example, superconducting quantum computing, neutral atom, photonic, etc. Well, all of those are still circuit-based models. So we have this concept called a universal quantum computing model, which is a model that allows you to perform quantum computation, and they're all defined in different ways, but they're all computationally equivalent. So for example, we have the quantum Turing machine, which is the quantum analog of a regular Turing machine. So the Turing machine was like the very first model of computation invented by Alan Turing. And so when people were first trying to think about quantum computing, they were like, let's extend the regular Turing machine into the quantum realm and use that for our basis as our quantum theory. But that turned out to be um, not very uh, not very easily understood or used to develop new algorithms, etc. So nowadays, most of our quantum models, like our algorithms, etc., we all think about it in terms of quantum circuits, which there's a universal gate set. We have qubits, and we use a sequence of gates to manipulate these qubits, and finally perform measurements on a qubits to get the answer. So topological quantum computing is unlike these other two models. So when we think about topological quantum computing, it's really not like a quantum circuit. So that's like a very major difference. It's a fundamentally theoretically different model that can't really be thought about easily in terms of logic gates, like quantum gates, etc. All right. So why topological quantum computing? So in regular quantum computing, or in the quantum circuit model, we have qubits and we have gates. And both of these, how they're represented physically is pretty important, because how they're represented physically uh, uh, means like depending on how they're being represented physically, the amount of noise and errors and decoherence can really impact the quantum calculation. So each gate you use on a qubit will introduce some amount of noise and could cause it to decohere. And um, so the idea is that what if we could encode quantum states globally, so non-locally, such that the global state of the system determines the quantum information that we're interested in. So um, one one global property of a system is its topology. So there's this classic example of a donut being topologically equivalent to a coffee cup, because as you can see in this animation, you can deform this coffee cup into a donut without like breaking it apart, etc. So that's the idea of global properties, like small non-local perturbations won't affect the topological properties of this coffee mug. So now, how do we apply this to quantum computing? And like, it's not like we can use a coffee mug to represent like a qubit or anything. So the idea is that we use we braid particles. So in this animation, you have two particles that are in two dimensions that are circling each other, and then the path that they draw through space-time. And you can see that path cannot be like changed without it passing through each other. And that's essentially the topological property that we're going to be encoding quantum information in. So I think this should become more clear once I start explaining what exactly I'm talking about. So the particle that we're interested in is called an enneon. And an enneon is not like an actual particle, it's a quasi-particle. So it could be like a collection of electrons that have this certain property. And very importantly, it's a quasi-particle that only exists in 2D systems. So you may be wondering, like, how is that possible that we live in a 3D universe? Well, there are certain types of systems where we can constrain like the degrees of freedom to only 2 dimensions. So uh, for example, like a very thin sheet of atoms, like graphene, which is like a hexagonal pattern of carbon atoms, is essentially constrained to just 2 dimensions. So even though we don't have like a truly 2 dimensional system, we can have these constrained systems in 3D that essentially act as 2 dimensional systems. And uh, there are certain things in 2 dimensions that are not the case in 3 dimensions. So specifically, the quantum statistics of enneons differ from both fermions and bosons. So, in 3 dimensions, we have these particles called fermions and these particles called bosons. And bosons are like the force carrier particles, like the photon and like W and Z bosons. And fermions are like electrons, etc. So an enneon is like unlike these um, because of their exchange statistics. So we have this equation, this like formula. So you have two particles and you exchange them in space. So this changes its wave function. So the amount of that changes is based on this value, this phase here. Uh, and for a boson, theta is 0. So you exchange it, the wave function doesn't change. And you exchange it again, doesn't change again. And for boson, it's pi. So then if you do it twice, then you return back to, so exchanging it twice means that it's the same as not exchanging it at all. But in 2 dimensions, it's different. In 2 dimensions, theta can be something that's not 0 or pi, which means that if you exchange particles in 2 dimensions and you exchange them again, like counterclockwise again, it's not the same as not doing exchanges. And the idea of this is represented in this image. So in 3 dimensions, if you have a loop around a particle, you can shrink that loop to a point by just like moving above because you have that extra degree of freedom. But we have a circle. If you have a loop around a particle in 2 dimensions, if you try to shrink it to the point without intersecting the particle, you can't do that because there's no degree of freedom that allows you to move the loop up or down. So this like means that there's like a fundamental topological. So this is a topological property of the system, and it just means that like if you have the loop not enclosing the particle, it's like topologically different than if it does enclose a particle. That's essentially the um, that's essentially why like why we're interested in this 2 dimensional system because of how these topological properties change. Does anyone have any questions so far?
Wait, so is the loop like the particle moving in the loop, or is it just like a theoretical loop?
It's just a theoretical loop. So we're talking. So it's just like imagine drawing a loop around a particle. This loop around a particle is different than the loop that's not around a particle in 2 dimensions. But in 3 dimensions, it's just the same. So, any other questions? Okay. So we want to encode the quantum information in some topological property, and we also want our quantum calculations to also be not sensitive to local perturbations. So we also want our topological, our quantum calculations to be done topologically. And this, so I already talked about like the paths the particles go in space-time. So imagine, so these two are two anyons in two dimensions, right? So you're exchanging them, so you're like rotating them around each other counterclockwise, and then their world lines, which is their paths in time. You can see the arrow pointing, so they swap places with each other like this, and then um, yeah, so this kind of forms a braid, and this braid is how computation is being done. And I'll go into more details about how exactly that works later. But as you can see in this animation, like you are rotating the you are exchanging the particles counterclockwise twice, but the end result is that you're resulting in this braid. It's not like you've done nothing by doing two counterclockwise exchanges. Another important property of anyons is that you can fuse them. So if you bring two anyons close together, you can approximate it as one single anion. And you just basically combine the quantum numbers and topological quantum numbers. So that's called fusion. So you can fuse anyons into another type of anion or into the vacuum state, which is like if you have anyons with opposite topological quantum numbers, if you bring them close together, it's like there's no particle at all, or so we call it the vacuum state. Or it could be another type of anion. So like these are like the three main things that we need for our anion model. So now we can go more into the specifics of how topological quantum computation works. So first you have a system, and you define a certain set of anyons. So we've got M, which is the set of different anyons that you have. So one is the vacuum state, and you have like A, B, and C, etc., which have their own exchange statistics. And then we have fusion rules. So if you bring two anyons close together, they fuse into a third anion, or maybe they'll fuse into like the vacuum state, or they'll fuse into one of the anyons that were fused. So n is the multiplicity. So that's the amount of ways you can get C from fusing A and B. Usually we just consider it to be 0 or 1. So you could say like A fusing with B can be 0, can be a 1, or it could be like A or C. And so that means there's three different ways that fusing A and B can occur. So if there's only one possible way, then the anion is called abelian. If there's more than one way, it's called non-abelian, which means that the result of fusing the anions is non-deterministic, which is really important for our quantum computation. So quantum computation relies on non-abelian anions, which means that once you fuse two anions, what you end up with is non-deterministic. You don't know which one you're going to get. Which means that essentially the fusion outcome are orthonormal states. So here you have the inner product of the outcome of fusing A and B into C, and the outcome of fusing A and B into D. And this is the Kronecker delta, so it's 0 if C and D are uh, it's 1 if C and D are the same, and 0 if they're different, I believe. And so they're basically like, it forms an orthonormal basis. And this allows us to encode quantum information. Oh yeah, it's called the basis forms the fusion, what's called the fusion space. So all the different possible outcomes of fusion is the fusion space. So how do we use this to actually encode a qubit? So a qubit in topological quantum computing is a non-local entity. It's not like a particle. It's a way that you fuse particles in order to you fuse anyons to get some outcome. So you can think of it as a qubit as a tree of possible fusions. So you can have A and B fusing into E, and then C and E fusing into D. So you start with the same set of anyons, you end up with this outcome, and then in the middle, the different ways that they fuse make up the qubit itself. So this isn't like a local property, it's a global property, which means that it's not sensitive to local perturbations, meaning that it's like not very sensitive to noise. Yeah, so a basis in the fusion space is given by like what order you fuse the anyons. So here's one possible basis, and you can like convert it into another basis using this F matrix. So, and these are topologically equivalent, which is why they represent the same state. So, so basically how the computation works is that you define a set of anyons and how they fuse, and you say like, okay, if they fuse in this way, then it's a 0. And if they end up fusing in this way, it's a 1, or something like that. And then to perform the computation, you exchange anyons, so which causes their world lines to like cross over each other, which forms braids. And then at the end, this like evolves the quantum system. And then at the end, you fuse the anyons and you perform measurement. And based on that, you know like which paths the fusion went in, and you'll be able to do the computation. I hope that was clear. Does anybody have any questions? Yeah.
So when you're just saying so let me think about this for a second. How to phrase this? You said fusing the anyons at the end tells you about like what kind of braiding they did before. Is that right?
It just tells you what the quantum state is. So like you don't necessarily know exactly what braiding operations were done, but like I guess you could figure it out by working backwards. But it's not like you know exactly which paths it took. But like, so the braiding evolves the quantum system, and measurement you read out the quantum state. So
okay, does this represent the non-deterministic like nature that you were mentioning before, or is that unrelated?
It is related because like depending on how they end up fusing, the measurement will be different. Any other questions? Yeah, it's probably going to be more clear if I show, well, it might clear things up if I show like a specific example of an enyon model. So we have here like what's considered like the simplest enyon model. It's called the Fibonacci enyon model. So there's only one type of enyon. Well, there's the vacuum state and one type of enyon, which is tau here, and there's one fusion rule. So fusing tau and tau, you can get either the vacuum state, so it's its own antiparticle, or you get another tau anion. So now so the qubit is represented by how the anions fuse. So one here is just tau. So yeah, in this case, 0 is the vacuum state and 1 is tau. So tau and tau, if they fuse to 0, into the vacuum state, and then vacuum state plus tau is obviously just going to be tau. So let's say this is 0, and then if they fuse to 1, and 1 fuse to tau again, so that's 1, And then this is just the non-computational state, which we disregard. And this is how we encode qubits. So it's not like a quantum number or a quantum or actual quantum state of a particle. It's encoded in as this fusion diagram. So how it fuses um, is what the qubit actually is. And to change basis, you have the F matrix. So this psi is the golden ratio, and then to braid a braiding operation, you have the R matrix, which is looks like this. And these matrices are different based on which anion model you're in. So this is just it for the Fibonacci anion model. And so if you wanted to exchange these two, you apply this, well, you apply the matrix. So physically you exchange the particles, but mathematically it would be applying this matrix to the current state. And so this is this. So the symbol here is e to the 3 pi I over 5. So yeah, and then here you apply like one after another. So you change the basis first and then you swap it. And then here is the equivalent quantum gate. So the Hadamard would be represented as like this braid, and then the X gate would be this braid, and the Y gate is this braid. So you shouldn't really think about it in terms of like our normal gates. It's, as I said, it's a different model of computation. So even though they're computationally equivalent, you can't really represent one-to-one with like a quantum circuit. So these are also approximations of these gates. Also, I should note that so Fibonacci ones are the simplest anion models, but it's also not there's also not much evidence that for their physical existence. So when we're talking about topological quantum computing, we usually are like for physically realizable topological quantum computing, we usually aren't talking about Fibonacci anyons. We're actually talking about Ising, the Ising anion model, which is what Microsoft is working on. So the Ising model is considered the most experimentally feasible anion model, and they're based on this type of anion called the Majorana zero mode. And in their recent press release, they said that they made progress. So how it's physically done is using a nanowires, and they found that their measurements were consistent with, but it was not definitive proof of MZM. So overall, topological quantum computing is still a ways away because we still have not experimentally realized non-abelian anyons. And once we do that, we can start like actually working on like making powerful quantum computers that are like not sensitive to noise. But for now, we're still in the progress of actually creating these non-abelian anyons. So in summary, topological quantum computing is a universal quantum computing model that offers inherent error resistance by encoding quantum information in global topological properties. And also, some problems can be easily represented in like with a topological model, such as this problem that's called the Jones polynomial solver, which results in more natural algorithms for these specific types of problems. Because in more pure mathematics, like there's something called braid theory, and as you can see, like the quantum computation forms braids. So it's like you can use this mathematical formulation of braid theory and group theory to work with topological quantum computing. And that's it for my slides, but I'm sure a lot of you aren't like things you are not clear on, so I'll hope that you guys will ask questions so I can hopefully make clarifications. Yeah.
I'm not sure if I missed it, but what is the advantage of using it this way compared to the classical quantum way?
So the advantage of topological quantum computing over our regular quantum circuits is that we are encoding quantum information globally, not locally. So think about like a braid that you have like physically. How do you undo this braid? Can you like move the strings around to undo it? So the only way to undo a braid is by either cutting it or if you like pull it out. But if you pulling it out means like going backwards in time, right? Because like it's the path that the particle goes in space time. So that's what makes it resistant uh, to errors because the quantum evolution is based on the braid, and if the braid is still there, then the quantum evolution is not going to change. So that's what, and um, error correction is like a kind of a pretty big overhead, right? Because you need more qubits to error correct, and those qubits also need their own error correction, and so on and so forth. So it's a pretty big overhead, which means that topological quantum computing is promising for error-resistant quantum computing. Yeah, yeah.
So earlier when you had like the wave function going to like to have a phase, yeah. I don't know. That made me think of like the e to the I phi or I theta. Makes me think of like the Bloch sphere and how when you rotate on using certain gates like I don't know, the Hadamard or the X gate, poly X gate. Your theta is defined as I think pi. In those cases, maybe for X poly X it's pi, Hadamard it's like pi/2 maybe, something like that. Is there any connection here to that?
So e to the I something is just representing a rotation, right? So if you're rotating around the Bloch sphere, you need the phase to represent the rotation. This you're like rotating a particle around another particle, so it's just a rotation, right? Yeah.
Wait, so is like the braid information stored in like the results, or how is it stored with this time?
Um. So the braid information like determines how the fusion is. So like okay, I don't have yeah. So if you swap anions here, they cross each other, and in the fusion diagram here, that represents like swapping this and this. So this changes the quantum state because the fusion diagram is changing. Uh, yeah. I I also have something here. So if you apply the rate, so you start with this state. So this is a state, right? You apply the matrix, it swaps B and A, and it like turns into something like this, and that changes the state. Yeah, and so this is another way of representing this. So if you want to swap this and this, you apply the R matrix. And if you want to swap C and B, then you have to change the basis first, and then apply the, well, you change the basis, and then you apply the the R matrix, and then you end up swapping B and Z. Yeah. Yeah.
So that's the same two steps here as on that paper.
Yeah, I
Just
believe
the
so.
label that all the. Okay. Yeah, I think that makes sense.
Yeah, because the matrices are represented like this, and yeah.
So then, follow-up question to my earlier question: is there any need for a block sphere in topological quantum gate representation, or is the relevant, is the relevant method for displaying quantum information these like little trees that you showed?
So, it's still like, just like 0 so one tree represents 0, and then the other tree represents 1, right? So the linear combination of that forms the block sphere. So you can still have a linear combination of basis states. Like, it's just the basis is each fusion diagram. So like, you still have a block sphere that appears.
Okay. Yeah, it's just weird to wrap my head around that. Like,
Yeah.
like the qubit isn't real anymore. It's not physical anymore.
Yeah. It's like the potential outcome of fusion, different fusioning of anions.
Is that why like you can have like for example in some places where you have like swap and then swap back because that actually does change them both?
If you swap and then swap again, the system is different than if you don't swap at all, right? Because that's like why we use like the 2D system instead of 3D.
Does that make it more resilient to noise for some reason? I don't understand. Like why?
Like what aspect of it?
Like what he was just saying. Like why do you need to make it so that if you swap them and then swap them again, it's not the same as if you didn't swap them at all?
That's how we make it topologically different, right? Because if you swap it and swap it again, and it's the same as not swapping, then you can just simplify this to just like 3 lines, because it would be topologically the same as 3 lines. So since we want them to be topologically different, they need to have this property. Yeah.
And did you say that how do you pronounce it?
Majorana zero mode. Yeah.
Did you say that they were a billion or not a billion?
They are non-abelian.
Okay.
Yeah. So abelian means that there's only one fusion outcome from fusing them. Non-abelian means that you have multiple possible outcomes from fusing anions.
For some reason I thought you said they were a billion. I'm like, why did they do that then? Like, why would that be helpful?
Yeah, they're not abelian. So basically, we have not experimentally realized non-abelian anions, but Microsoft made progress on it, which is somewhat significant.
I heard there were questions though as to like their methodology and stuff.
Yeah, the main thing is like in the press release, they're like, we have created topological qubits, but then in their actual article, to Nature, they're like, we have consistent evidence consistent with Majorana zero modes, but they have not confirmed they have. So they kind of overstated the importance of what they've done. So that's why it's like controversial.
I've heard there's even a possibility of just random noise that they were detecting.
I mean, it could be like we don't know for sure. So yeah.
Maybe it's dark matter or something. Like that would be sick. I have a more like physics, I guess, influenced question. So so anions I don't know. You might not know this. I think from what I know, anyons means that you can have any any value of like spin. Is that accurate? I don't remember.
I think it's like any value of this theta here. Yeah, instead of just 0 and pi.
Because I'm thinking of like, you have anionic statistics, and that's different from fermion and bosonic.
So for bosons, theta is 0, and fermions, it's pi.
Right. And for anions, it's any.
It could be something else. And like only 0 and pi are possible in three-dimensional systems.
Okay. And then I guess I'm just thinking of like fermions and bosons. Like if you look at I think like quantum mechanics or statistical mechanics, you can get you can get some value that represents like the spin of those things, and that's why electrons have like only half integer spins, and then I don't remember if those are fermions or bosons, and then photons or something are only integer spins. So that was just a unique perspective there.
Yeah. I could talk about like, yeah, so anyons could appear due to the fractional quantum Hall effect. There's also superconducting nanowires, which is what Microsoft is doing to create Majorana zero modes. There's also other physical processes. In condensed matter systems. So yeah, fractional quantum Hall states, spin liquids, topological superconductors. Yeah, I don't really understand this stuff, but yeah, if you're interested, you can look into that.
Yeah, if you guys like that stuff, talk to Arnav Banerjee. That is, I think, everything in his research. He's in the physics department. He taught my statistical physics class. He's very interested in all this stuff. It's a lot to handle.
Yeah.
Yeah, so here's like what the Ising model looks like. So you've got a fermion and an anion, and this anion is the Majorana zero mode, and this is how they fuse. Yeah, they correspond to Majorana zero modes. The fermions are, I don't know what this means, but you know, they're. I think these are experimentally realized, but the main thing is that we need to find Majorana zero modes, which is what Microsoft is trying to do. And so F matrix, for changing basis, R matrix for exchanging or braiding, and then oh yeah, and then for Ising, so if if the two anions fuse into one, and this one fuses into one, this fuses into one, and all of them fuse into one, then it's 0, 0. And like how they fuse is how you encode the quantum information. Uh, and you can also represent quantum gates using the R and F matrices. Yeah, so
you say that they could like approximate this quantum gates or like be exactly like them?
So for the Fibonacci ones, I believe it's an approximation. The paper I found that image run, they use like an ML model to approximate uh, the gates with braiding operations, but like it's just not an approximation. Yeah.
Wow, it says temps to rise. Even warmer.
Yeah.
Oh yeah. I was like, where's it saying that on the paper? Like,
And also, technically, the Ising anion model is not universal, but you can add another gate that's non-topological to make it universal. So, yeah. But the Fibonacci one is universal, but there's no like experimental ideas about how you could do it. Yeah, so for measuring, you just bring the anyons together, and then you measure how they each fuse, and then based on that, yeah.
And you can control the initial state of the anyons.
So in the beginning, you have this starting set of anyons, and then you say that we are going to fuse them in this order, and then uh, when you're doing it, you swap whenever you do the swapping operation, etc. So yeah, you do control the starting state. Like the starting state is how how they could uh, how they could fuse. So yeah, that's defined by how you define the model.
Okay, that makes sense.
stuff.
I mean, they look like shoelaces, and you trip over your shoelaces.
Yeah. Also, the reason why Fibonacci anyons are called Fibonacci anyons is because of how the number of ways they can fuse grows by the number of anyons you have. So yeah, 1, 2, 3, 5, etc. Um, and this is unclear whether it can be ever realized in a laboratory.
Was this published before or after Microsoft?
It's definitely before. Like Microsoft was only like a couple months ago, right? 2017. Yeah, and this is the thing about the loop needing to pass through the particle, like exchange statistics. Yeah, because like if you're moving the particle around to the other side, you're kind of like drawing a loop around it. So like if a particle is going here and then you go back around, the path it traces a loop, and you can shrink that to a point, which is like it not having moved at all. While in 2 dimensions, if you go around and back again, you try to shrink the loop down, you can't do that because it'll cut through the particle. So they're topologically different.
I find it funny how for some things having less dimensions is helpful.
Yeah, it's like having constraints means that like there's more possibilities, because if you have less constraints, then you have more things that are the same. So yeah.
Is it good to conclude here, maybe? Conclude early a little bit. Is that all right?
Yeah, that's good. Yeah, thanks everyone for coming. Hope you guys found it interesting.